We're now in a position to write down what we observed numerically. We'll work in the context of Markov chains that have the fewest complications. They are very well behaved, finitely many states only. Irreducible, you can get from anywhere to anywhere else on the state space. And aperiodic, no cyclical behavior. In this situation, we have a long-run behavior that we observed numerically, and I'll start writing it down as a math fact. So you take any state J and you look at the n-step transition probability, which we are calling P sub n, and let's just say it's the chance that you end up at J in n steps, given that you started at I. If you look at this transition probability and you let n get large, then we saw that this probability converges. And I'm going to write the limit as, if you like, a function of j. It depends on j alone. And already we have something interesting, because in the limit you don't see I. The limit is the same regardless of where you start. That is what we saw. The long-term probability of ending up at state j is the same for every starting point I. More is true. This limit pi j is strictly positive, and when you put all the pi's together, you get a probability distribution. That's what we saw by computation. We actually computed those n-step transition probabilities. We took the n-step transition matrix and we raised it to larger and larger powers, and eventually all the rows were the same. Now, each row corresponds to a different starting point. So if all the rows are the same, then the starting point doesn't matter. And that is what this mathematics is saying. Now, this theorem needs a proof, which we're not going to do. It's a consequence of the Perron-Frobenius theorem of mathematics. You've seen it in numerical examples, and you can create your own transition matrices that have these properties. Go through the numerical calculation and you will see this settling down to what is called a steady state when n gets large. So accept this, and let's talk about some properties and some consequences, because this long-term distribution is a useful object. What I'm going to do now is state the properties and talk informally about them, and then in later parts we'll establish some of them. So the first thing to note is that this limit distribution is unique. And it can be calculated well. I mean, you can calculate it by doing what we did, which is taking the n-step transition matrix and raising it to a power. That's very heavy lifting. It turns out that pi can be calculated by solving a set of equations. And the equations are pi is equal to pi times p, where p is the transition matrix. this needs a proof. We'll look at it later. For now, I just want to explain why this matters. It matters because we can get hold of pi without going through, in many cases, we can get hold of pi without going through a numerical computation. It's worth being clear on exactly what pi is. Pi is a vector in which I have collected all of the pi j's. So if I imagine the state space to be 1, 2, etc. up to s, or at least labeled by that, then since we said that for every state j there is a pi j, then there is an s vector pi that we're imagining. And that vector solves this set of equations. That's one of the things we're going to prove. The importance of this is it helps us calculate. Now, take a look at that set of equations. There are s of them. There's one for every element of pi. Doesn't the vector 0 satisfy those equations? Yes, it does. The vector 0 satisfies those equations, but that's not a probability distribution. We're looking for a probability distribution. If a vector pi satisfies this equation, then clearly 10 times pi satisfies the equation, 15 times pi satisfies the equation. But there's only one that's a probability distribution that satisfies this equation. The probability distribution has to add up to 1. Right? So if you multiply by 10, it's going to add up to 10. It's not going to be a probability distribution anymore. Next, the theorem says that in the long run, the chance that your chain is at j is about pi j. So pi can be thought of as some kind of long run approximate distribution of the chain. But if the chain actually achieves this distribution, if it actually gets there, then it stays there. If the distribution of your chain is pi for at any time n, then it remains pi after that, and that is why pi is called the steady state distribution. Also the stationary distribution. We'll establish this too. And finally, third property that we're going to use is our limit theorem says that if you run the chain for a long time, then the chance that you're at j is roughly pi j. Well, if that's the case, then in the long run, you're going to spend approximately pi j of your time at the state j. the long run expected proportion of time spent at j is equal to pi j. So these numbers pi, the elements of this distribution, have several interpretations. The two crucial ones are that they form the limit distribution of your chain, and they measure the long run proportion of time that your chain spends in various states.